with great pleasure that I welcome Saeed Zaghloul here to Google. 4 years ago, I was starting at university, and he was a Fulbright scholar to the US, and he told me, young man, study computer science, so I'm happy to have him here at Google 4 years later. Thank you. And what Saeed will be talking about today is the next generation of all-IP telecom networks and some of the challenges and issues that come with what is really a very exciting development, especially for us here at Google. And this talk will be based on papers, several papers, one to IEEE Letters on Communication, and also his presentation recently, actually 2 or 3 days ago in Las Vegas at the Consumer Electronics Conference. So very excited to have him. And let's see, a couple more words. After he was a Fulbright scholar in the US, he was a telecommunications design engineer, do I have that right? At Sprint Nextel. And he's currently a PhD candidate at the Technical University Carolo Wilhelmina of Braunschweig, Germany. So.
Thank you very much, Adam. Actually, I have my mic here. Thank you. So it's an honor and pleasure for me to be among you today to present my a tutorial talk that is based on my PhD research, based on a couple of papers, IEEE Communications Magazine paper, and another recent paper that was presented in the IEEE CCNC conference that just took place last week. My name is Saeed Zaghloul again, and this work is based on my work with Professor Admila Yukan and our collaboration with Dr. Wissam Al-Ankar from formerly with Sprint Nextel and now with Booz Allen Hamilton. To give an idea about our location in Germany and our group, we're located here in Braunschweig, basically very near to Hanover, half an hour away from Hanover, and about west of Berlin, about an hour and a half by the train. It's quite nice there, and there's a lot of history in Braunschweig, so I encourage everybody to go there and visit. The Institute of Data Communications and Networking actually is basically composed of 3 major groups. The major groups that we have are the Embedded Systems Group, the Space Communications Group, and the Networking Group. The networking group where I work at is composed of 2 subgroups. One that is optical control plane, ones that's interested in optical telecommunications research. Another one that I work at is basically concerned about 3G, 4G, and mobility issues, design and architectures. So our today's presentation outline is actually composed simply of the motivation, the background of this presentation, a little bit about the next generation, an example actually about next generation IP multimedia subsystem services, what's IMS, the big buzzword that is taking place, and we hear a lot about it, but, I'm here to demystify it a little bit and point out some issues. I'm going to use an exemplary service actually to demystify IMS and point out some issues, and then talk about some architectural challenges in IMS. The architectural challenges that I'm going to be talking about are related to call setup delay, handoff management, and quality of service profile unification. A little bit point out about each of these challenges, and then at the end of my presentation today, I'm going to make some conclusions and point out some future work and research. So the objective of today's presentation is basically, as I just mentioned, is to really investigate, the challenges and the deployments of next generation systems that are totally based on the IMS platform. That is really a revolution, actually, from the current or the traditional sense of telecommunication networks, where you just have your phone and just make dial a number and do call forwarding and have very simple services. The future is all about value-added services, location-based services, having some cool applications like, actually, I remember from my last conference in Las Vegas last week, the Nokia's VP was there, and he was mentioning point-and-find applications where you could point your handset to some really nice site, for example, the Eiffel Tower, let's say, in Vegas, and you want the network, you want to get some information about that Eiffel Tower. Say, okay, I'm there, but I want to know a little bit more about the history of that thing. So I just hit a button on my phone, and the phone will just get me the wiki page about the replica Eiffel Tower in Vegas. Of course, this involves more than just simple image processing. Maybe it needs to involve also some location-based service, so the system doesn't really miss it with the real one, basically, in Paris. So things like these are basically quite new, non-traditional form of services that we are kind of looking at and imagining for the future. Our approach for this research that I'm doing, and more or less focused on quality of service issues. The approach is mainly about, because I worked and collaborated with Sprint, so we're taking, as an example, the EVDO network from Sprint, the cellular network, and basically looked at the signaling that takes place in the network from an end-to-end perspective. So that's what I'm going to be using. So all the references, all the naming conventions, even though in a large sense, in the large picture, will apply to many other networks, the terminology and the jargon that I'm going to use will be more or less taken and adopted from the 3GPP2 or the EVDO network. The results that I'm going to show simply, basically, we're going to be identifying some issues and basically proposing some optimizations for how to make things better. So that's my approach today. So to make things more just clear about the future trends for the telecommunication networks. So the future trends actually are based on basically from. We can look at it from two perspectives. The first perspective is really the network architectural level, where people are looking at higher bandwidths, basically. We want higher access rates. We want different access technologies. We want to deploy certain IP core in the network, and we want to reuse that core for, let's say, we want to have WiMAX, Wi-Fi, cellular networks, all connecting to the same core and reusing the core over and over. We don't want to deploy a whole big separate networks, that are separated from each other, and we want more or less flatter plug-and-play architecture that will just plug and play to that core. From the service level, people are talking, as I just kept mentioning, IMS, which I'm going to explain shortly. From the service perspective, people want to deploy that new architecture, this IP multimedia subsystem architecture. And basically, this architecture really allows third parties to get into play. It's just not designed for big providers and big telcos. Third-party providers really mean companies like Google, who have real high experience in basically making really consumer-targeted applications, nice things like with Google Maps, location-based services, pushing some specific advertising to the end user that really suits him. So it opens the door really wide open, away from standardization bodies, to the users, basically, to the third parties, to basically offer their nice value-added services. So that's basically what we mean by this development at the service level, and that's quite important. And then really we're talking about richer multimedia session, having video, online gaming, all sorts of the applications that we all hear about in the media. So it's more about involving third parties, having richer sessions, and having enhancing the end user's experience about the network. So the challenges now that we're going to be talking about actually today are simply related to the fact that as the telecommunication networks grow, telecommunication networks are not really simple networks. In fact, they are networks of networks, actually. To illustrate that fact, actually, before continuing with this slide, As we can see, in the past, in the old days, in the 90s and late 80s, people used like cellular networks just to make, a radio phone call, voice, end-to-end voice call, And that was basically your base station and radio network controller managing multiple base stations, and that's it. There was no concept of internet connectivity over your handset, and things were simple. Afterwards, as this network evolved, we had this we added the IP support to basically the radio network. So we added the packet data serving node as the first IP gateway element, supported by the home agent and the authentication authorization server to basically allow authenticating and authorizing that session. PDSN and home agent really support your IP mobility. Basically, if you move between multiple PDSN regions, as I will show in this presentation shortly, basically mobile IP will handle your mobility. So as you move, your session won't be interrupted, because you will not change your IP address. Finally, people recently, like in the last few years, really added, they wanted to focus more. It's not just simple IP connectivity. It's not simple, just voice calls. We want to focus more or less on the service itself. We want to differentiate services, and we want to have different third parties getting into play. That's why people introduced the IMS. The IMS includes multiple components. I'm just going to say the acronyms now, and we're going to look at each one of them quickly. The first ones are basically the proxy call session control function and the serving call session control function. These are simply proxy and basically proxy and SIP registrar and servers. You're all probably familiar with SIP. And then we have the home subscriber subsystem, which is basically the database, the part basically, or the element that manages the user's profile or database. And then we have basically the application servers, where these application servers, where basically the third parties can get into play and interact with the IMS network. So through this application server, you will be interacting with these elements to provide services to the end customers. So the IMS is simply an enabling framework for you guys, and then you deploy your services through using these SIP application servers. And the system will handle it for you down there. But the whole purpose of this presentation, why do we want to understand more about the semantics of the telecommunication network? You want to write application. You want to understand what's happening underneath, because there are some specific things. There is this mobility, basically, in the network, and there are some specific things that you want to be aware of. It's not just like a connected network, but there are more dynamics in the network, as we will see shortly. And at the end, there's this policy control and charging function, which we will focus a lot, actually, on. And this policy control and charging function will basically interact with these two networks, the radio access network and the IP network, transport network, to push and authorize for the use of the services. So that's I guess, a quite important box here to add. OK. So continue with the challenges. As I mentioned, we're talking about post-dial delay, the challenges that we're looking at. Post-dial delay is basically the time that whenever you dial for a service in your handset, the time that it would take to establish this call. That's a very important telecommunication network parameter that you don't want it to take too long time for you basically to acquire the service from the network. That's even more important for push-to-talk services. You don't want to wait for like a minute to reach the other parties. The other thing is basically when you're moving inside the network, as you hand off between areas, you don't want to have too much session interruption. Currently, it's about 70 milliseconds with voice telecommunication networks, and with IP networks, we're talking about seconds ranges. And people are working on reducing that down to that, to the level that we experience today in current wireless networks. There are multiple design and challenges actually in deploying the next generation networks. And these multiple design alternatives that we have in terms of these policy functions. We saw on the previous slide that we have a AAA server, authentication and authorization server, authorizing for this IP network, authorizing for this radio network. And we have this policy control and charging function authorizing from the service perspective. So we have two policy functions. And we're trying basically to minimize these conflicts basically in the roles of these policy servers. So what is IMS all about? I kept talking IMS, IMS, IMS. So just to make it clear, give a clearer definition of IMS. IMS is really an access agnostic framework. It doesn't really care. It's designed to be not to care about the underlying network, whether it's wireless, whether it's cable, whether it's cellular of whatever kind. It shouldn't really care much. The second thing is IMS really deviates from the common principle that we all followed in the past, which is actually quite strange. It was quite strange to me when I learned about it initially, like a long time ago, that people really standardized even the services themselves. You'll have a standard from ITU, the International Telecommunication Union, that tells you how to do call forwarding to that level. They standardized each service by itself on its own. And to build a service, you have to go from you have to build the routing functionality, you have to build security, you have to build everything. So it's a nightmare, actually, and we don't like that. So to avoid that, what we did is basically introduce IMS to have a horizontal architecture where you just only focus on the service itself. So that's avoiding this stovepipe, the so-called stovepipe architecture. And then you want to interwork more and more with other service platforms. Like service platforms, there are already call forwarding functionalities that are already, and other functionalities in the network, like call parking, call forwarding, etc. And these functionalities are already deployed. We don't want to throw them away. So we need to interact with them. And that's actually achieved through the use of these application servers. IMS is also an open framework, mainly based on SIP and other frameworks like H248 and diameter protocol for authentication. And IMS, needless to say, will be deployed by most of the major standards, like or major standardization bodies like the Third Generation Partnership Project, Third Generation Partnership Project 2, and WiMAX. To show a little bit about how the current 3GP networks are arranged, our handset is basically connected to a base station. The base station is managed by a radio network controller. The PDSN, the radio network controller's traffic, is forwarded to the packet data serving node, forwards your traffic and tunnels it. And the PDSN basically is your first IP node. This is the first node that really talks IP. It's like your router, basically. And then through the interaction between the PDSN and the home agent, you get mobility. So if you move from one PDSN to another, you still connect to the same home agent, and then you have mobile IP functionality. And then the AAA really authenticates and authorizes your connection, and it returns to the network, to the PDSN and the RNC, your quality of service profile. This quality of service profile is completely transparent to your use, to the service that is being used. It doesn't understand whether it's a gaming application or a voice over IP application. It only knows that you have a maximum amount of 1 megabits per second, let's say, maximum aggregate bandwidth. You can do these certain profiles, but really doesn't understand what's happening beyond that. So it's almost static. So that's the max that we can do on a AAA. With some tweaks and tricks here and there, maybe you can get a little more, but it's not really aware of the service that is running. So the quality of service that we're talking about, this quality of service profile that is returned by the AAA to the PDSN will be enforced by the PDSN on the IP layer and by the radio network controller and the base stations from the RF perspective. So that's that's how we really enforce quality of service. So let's remember this, just to recap. AAA provides the quality of service profile, and PDSN enforces it at the IP level, and radio network controller and base stations enforces that at the radio level. Simple. So we talked a little bit about the three network tiers, or the three networks: the radio access network, the IP transport network that included these elements, and now we're going to look a little bit more about the IMS elements that I've been talking about. So the IMS elements that I talked about are these call session control functions, be it proxy or serving call session control function here. And the proxy function really does message verification, just like any SIP proxy with extended functionality. It verifies the message whether it's correctly formatted or not. It generates accounting for that service and sends it to the AAA collection for collecting that billing traffic. And it authorizes and it interacts with the policy control and charging function to authorize for that service. So your requests simply go from this handset. If you send a SIP request, your first entity that will interact with that SIP invitation request will be this PCSCF. And then it will, if it's fine, it will be proxied through an interrogating CSCF. It's another layer to separate between domains, another SIP proxy. And then it will be proxied to your serving SCSCF or your SIP registrar. And it will be definitely authenticated through your home subscriber subsystem for basically, depending on your service profile. If you're requesting a service that you're not subscribed to, you will be rejected. If you want to deploy any value-added services now, it will be deployed through this SIP application server here. For example, say that I want to, say in a parental control application that we're going to see in a second, I want to say, let's say, I want to restrict my child from making calls during school time, but only after school time. So what will happen is that once your invitation request, or basically the call establishment request, goes to to your serving server here, it will be routed through this SIP application server to figure out whether this is the correct time or not. If it's not the correct time, it will reject it. If it is the correct time, it will just let it through. So you can do any fancy things. We can have actually a lot more applications, like maybe this, you can deploy a lot more like location-based services. If you're in that location, you can allow certain things to happen. If you're in the school range, you can only call your mom and maybe your teachers. If you're at home, you can call everybody. Any kinds of things. So just to recap things and to put things in a bigger picture here, we see a whole call setup scenario. And this call setup scenario that we have includes the three tiers that we just mentioned and the steps for making a simple call. The steps for making a simple call are basically requesting the service from the IMS framework. That's step number one. Step number two is basically requesting the radio resources from the radio access network to allow that service to happen. Then having some authorization, service authorization in the network to authorize for the use of the service that is being requested, and to authorize for the radio resources that are being claimed from the network. And then in the end, once everything matches, and if what you're requesting is what you're really authorized for, then we get basically your media session established. So these are simple 5 steps that summarizes how you establish a simple session. So we saw, in summary, there is interaction between the user to the IMS network. There is an interaction here. The user to the radio access network, that's another interaction. And there is some gluing between both of them through these 3 and 4, basically for authorizing that service, basically having the IMS controlling the bearers, the IP and the radio bearers. This is called service bearer control, where the services really control the radio and the IP bearers. The bearers means that the transporting mechanism. So we talked a little bit about the AAAs being the policy servers that basically manage the underlying networks, manage the underlying IP network, and manage the radio access network. And the PCRF was the gluing element or the policy server that allows services to control these two underlying networks. So what does it do? It really authorizes the quality of service, the quality of service level for your request from a service perspective, and signals that down to these two networks. If it needs to be updated, say you acquired more bandwidth for some reason, the network load reduced, it updates that. If you run out of quota, it terminates your session, and so on. So it has control over that bearer. And it also, furthermore, supplies the charging rules that are relevant to your service. So it's much more aware than just the simple AAA who just statically knows this bandwidth and that's it. That is just based on your subscription. So let's see this parental control application that is based on our Communication Magazine's article in the September issue. So this application is simply having a parent. Her name is Sarah. And Sarah wants to restrict her child, Bob, from calling his friend Johnny during school time. And only after school time, Bob is allowed to make the calls to Johnny. And furthermore, she restricts the quality of service for the video to be 32 kilobits per second. She doesn't want to pay much for the video access. So she wants to limit the options that Bob has. So to do that, she configures basically the access rules using a web portal, and these access rules get saved basically into the network, basically in her HSS profile, and configures these rules that will go to the application server, as I just mentioned in a few slides ago, about how this call request will be treated. So what happens when Bob wants to make a call? When Bob wants to make a call, Bob simply sends a SIP invitation request. This SIP invitation request is received by Johnny. This simply triggers basically some authentication and authorization through interaction between the policy control and charging function and the application servers and the call switching, call session control functions in the network. So it just authorizes you for that service. And then afterwards, what happens is some similar authorization takes place on Johnny's side. We're not showing Johnny's side. Afterwards, what happens is that Bob starts requesting these resources from the radio access network in parallel. And then the request will be pushed from the radio access network to the IP network. Once the IP network, this PDSN receives all your authorization information from, it knows already your subscription profile from the AAA, and once it receives it from the policy control and charging function here, it's going to authorize for your service. And then if you're authorized, your media session will be established. A better picture, I have a clearer picture than this in the next slide, but this is just to show the steps that all what you really need to do is basically send the request, authorize for that request from the radio network, compare your authorization from the service level, the radio level, they match, boom, session is established. That's as simple as it is. But actually it involves many, many, many steps because we're talking about signaling on 3 networks. So this is, again, a simple recap of the previous signaling that I showed on the picture. And this is more or less SIP signaling that we're all familiar with. So this is the invitation message that I talked about. And this basically triggers the service some service authorization information coming from the proxy call session control function, because it receives your invitation request and pushes that service information to the policy control and charging function. Now for this side, we have two options. Once I receive it, I receive this service information at the PCRF. I could simply push it to the PDSN directly to the access gateway, or just can hold on it. Maybe because what if the call request doesn't complete? I don't want to reserve more resources in the network. So what happens afterwards is that this provisional acknowledgement that we're all familiar with will trigger radio bearer request or reservation from the radio access network. We'll try to acquire the radio resources for the session from the network. And that's through EVDO or access technology specific reservations. In EVDO, there is a procedure to request that. In UMTS, there is another procedure. So that's the procedure, the reservation procedure that would take place in the radio network. Once that completes, you're done here on Bob's side. But since, for example, on John's side, the PDSN doesn't know yet about your authorization from the service perspective, when it receives your EVDO bearer reservation request, when you're claiming the radio resources, what happens is that the PDSN will contact the PCRF and ask it, hey, I'm receiving a service request for that quality of service. Is he authorized? The PCRF may have the full information already from that step, so it may not need actually to contact the PCSCF or application services. And it may not. For some reason, may need more information depending on the requesting PDSN. Maybe you're restricted in certain regions. You have some restrictions based on where you're accessing that service at. So it may and may not do that. Once you're authorized, you confirm the service, and then you continue with the standard SIP signaling with, this is called SIP with preconditions, actually, for telecommunication networks. You update and continue with ringing and acknowledgements. There is a part here that is basically once you receive this provisional acknowledgement here after the ringing message, there is a trigger that comes from the proxy call session control function down to the PDSN and through the PCRF here, and that request instructs the network, the IP network, from the service. You see this is the IMS, and this is basically the service really is basically in charge. And it's not only the PCSCF, because this is just an illustration figure. It could be your application server, your Google's application server. Yes, sir?
So assuming that you have your application server and your proxy must send all the parameters for the invite to your application server, how do you ensure that, for instance, I will receive the location of MT initiating a call? Is there any specific protocol? Is there any standardized extension? Let's say that Google wants to deploy an application which will be aware of the location of the place where the call is originated. What kind of guarantee what kind of protocol would you use to pass this to us?
So the question is, how would during this call setup procedure, how would this PCSCF or application server know the location of the handset, basically to establish the service? There is a lot of work actually going on today with the presence servers, and in that region there is a lot of standardization that is taking place to acquire the service through the presence platform.
But I will not get access to the presence server because this is something which the telecommunication provider will keep for themselves. I would understand that I will have extra parameters added to the original invite message, right? Because I will not get access to the location information of all the cell phones.
True. Actually, this was one of it is a very interesting point. Actually, it's how to deploy IMS. We had actually a IMS workshop last summer in Greece, and that was one of the main things actually with these application servers, even interacting with your database as well, your HSS or your presence information. Again, the solution to that is, as I'm aware of, is not there in the standardization bodies yet, but it really depends on the SLAs that you have. You may even end up having some application server like brokering between you and the provider during the setup stage. Did I answer the question, or?
Yes, so there would be like a custom proprietary.
Some broker, yes, some broker application server to basically isolate you from directly accessing user-specific information, only giving you the specific parameters that you need.
So pretty much it means that only big players can deploy services which are really rich in new features. Because if you are a small startup company and you want to do something by yourself, you will never reach the SLA on the signalization level with any provider giving you such information? Because they will tell you that this is a privacy issue, that they will not.
Actually, this is contrary. This is a very interesting question here. But the whole point is actually that providers or third parties here get into the play by just maybe owning this application server here. There was a nice startup company from Holland that was just doing SMS, some next generation SMS services, and they only owned their application servers there, and they wanted to interact with the providers. And the whole discussion that triggered was they wanted some access to the home subscriber subsystem directly, and the question that popped up, oh, how come you're going to just immediately access my provider's users database? You could just simply just even, like do, just search everything and get more information than what you really need. So the answer to that maybe through some brokering or through brokering. So you basically isolate them from directly accessing the information that they don't need to have. That's a very interesting question. So. Again, this is an excellent question, actually, because it really gets us to the issue, actually, of even this presentation. The whole point that I'm making about the challenge and quality of service is that, okay, all of these guys are trying to get into play and make, and basically deploy these services. This means that there is really, you cannot control things by standardization in terms of the delay that will basically, how long will it take really to get this information. Suppose that this service composed of many collaborating or federating providers, small providers to complete this service. One is managing your location, another one is managing the number of your calls, and etc. A simple example that just comes into mind.
My point is that 20 years ago there was TCAP, and TCAP query were supposed
Yes.
to replace and fix all of those issues. Now we have an extension to the SIG, but it doesn't really exist yet in the form of a specification, and we are again the same.
Yes, actually that was, at that time they had this TINA-C, which was really ahead of its time, but unfortunately because we were not prepared for it, it didn't really fly. And IMS is really based on these principles, more or less, but really taking over all the powers from IP and from SIP. That is really very successful. Two very successful technologies, and just pushing it. So just to show just a little bit of how complicated it is from the radio perspective, things are basically if you receive, that's from the radio plane perspective. So how the radio basically, how you reserve quality of service on the from the radio level. This is the downlink or from the base station to the radio network, to the user. So you receive your packets here. And these are basically the filtering rules that tells, there are filtering rules that are provisioned at the PDSN, at that IP node here. Here's the PDSN. That PDSN that was provisioned with these rules from the PCRF during this call setup. So these rules will instruct the PDSN on how to separate traffic and between who and who. So it will separate traffic using simple, it looks like simple access lists actually that are dynamically provided to the PDSN. It separates traffic. And this traffic is separated at the PDSN level, and again mapped to tunnels between the PDSN and the radio network controller, because the radio network controller, unfortunately I only have RAN here, but the radio network controller is simply doesn't understand IP, so that's why we tunnel it into these so-called A10 tunnels, and then once this traffic is forwarded, it will go down and get mapped again to the radio link protocol flows, basically, and which goes down to the user. So it's really complicated, and this is just a simplification of how things go. So enforcing quality of service really means that we want to enforce quality of service in all layers, in the IP network and in the radio network. And we signal that on 3 levels, at the radio network level, at the IP level, and from the service level. Okay, so the challenges that I just mentioned in the very beginning of our talk here today is the post-dial delay challenge, the handoff delay, and the quality of service profile unification. So, the challenge is really with the post-dial delay. The game there is basically, because we have this very long we have so many messages, it takes quite a long time to establish the call, about 10 seconds in today's networks, from today's network's perspective. The game to optimize it is really based on two main things. The first one on how fast I can acquire the radio access network, and I will explain why shortly. The second thing is reducing the message sizes that I'm exchanging with the radio network. So two things: how fast I can acquire and the message sizes. We optimize these two, we minimize the call setup time. So this was one of the measurements and tests I've done with Sprint Nextel, with our collaboration with Sprint Nextel. And this is mainly based on reducing the call setup delay through optimizing radio network parameters and optimizing SIP. Optimization of radio network parameters is really because your handset is not on all the time. It goes dormant. It releases the radio resources as you're not using it, because it doesn't want to keep reserving very expensive bandwidth. That's how most of radio networks work. So to basically, when you want to initiate a call, what this means really is you want to reestablish that traffic channel with the radio network, and then send your initial messages. On the receiving side, the handset is not there yet, and it needs to check whether it's having any message or not. That's periodically checking the so-called paging channel. So the whole game is about really acquiring, really minimizing that time. So there are mechanisms in the EVDO network called enhanced control channel, where you can acquire control very quickly. It saves us about 100 milliseconds from the current 9 seconds delay. And doing some data, sending data or data packets over the signaling channels, over the control channels that are always alive, that you don't release normally. So we use these tools to send the first invitation message. So we save about 370 milliseconds. On the receiving side, there are about 5 seconds. Every 5 seconds max, you keep checking whether you received a message or not, whether you received an invitation or not. So it may take you, on average, 2.5 seconds, the average of this 5, to basically to figure out whether you received a call or not. So we reduced that actually to this 426 millisecond cycle. Okay, it will be at the expense of the battery lifetime, but that's the best we can do. And then this basically ended up killing about 3 seconds out. So that's just simply by using and acquiring how fast we can acquire the radio channel. On the other hand, we wanted to play a little bit with SIP by reducing the SIP content. Not all the STP content is really needed by the radio network. We kicked out some of it, some header informations, and that really reduced up to 5.4 seconds. And then our real target was 4 seconds from the ITU E771 standard. That's the standard for national calls, and that's what we were testing for. So to do that, we wanted to be a little more optimistic about the call establishment. We said, okay, we will do aggressive signaling by saying we will assume that the radio network will always establish its call. So if we make this assumption, we don't have to wait for the radio network confirming its reservation, the establishment of the call, and sending the ring tone immediately to the sender to the sender. So that may end up actually having some ghost rings, basically, if the other side didn't really establish. So that's the trade-off of it. To look at things more of like in a chart perspective and how things work, really, the same results of the table, but per message. So the invitation message is clearly the worst one, because it's a little large, number one, and it really involves accessing the network for the first time and establishing the traffic channels. So this is really where most of the radio optimizations were really beneficial to us. For this invitation message, mainly, because it's the first message we're sending. And the SIP and the size of the messages for these little large messages, because they carry some SDP inside them, we basically benefited from that by these amounts, by these pink amounts over the air interface. Further challenges here, I just want to be a little quick about it. This quality of service profile, we want to unify our quality of service. We have two policy managing servers, the AAA and the PCRF. We want to unify both of them, and we want to reduce the amount to take a handoff. How does that happen? Currently, we have this AAA managing the PDSN and the radio network controller, and we have this PCRF talking and managing the policies from the service perspective. We want to reduce this management overhead, actually, and have only a single quality of service profile. So what we do really is have the PCRF basically as our managing policy management profile, kick out that AAA functionality, and have currently, as I mentioned in the very beginning, the IMS is really a service agnostic network. And using this, if we want to have some network-specific parameters that the AAA used to handle, this means that we want to introduce, this is controversial of course, some network-specific parameters or profile for each network inside this HSS. So whenever you want to authenticate from an EVDO network, I get this configuration-specific information from the HSS, pushed it down to the PCRF, and this will configure both your PDSN and your RNC for your network setup phase. So that was one of the things, but again, it's controversial because some other people will tell you, okay, I would like to maintain this separation as much as possible. I don't want to maintain multiple profiles. But the benefit of that is reducing the management hassle and conflicts. So that was one of the things that we proposed actually for quality of service profile unification. The other challenge is really for an established session. For an established session, if you're a moving user inside the network, it will take actually quite a long time as you move between PDSN regions. Just to show that in this diagram here, you're connected through that call setup that I just showed. And as you move from one area to another, the same signaling takes place. You want to authorize. This PDSN doesn't share necessarily context with the previous one. So it needs to authorize you again to figure out with your PCRF to grab your service-specific quality of service profile to figure out who you are and whether you're authorized or not. And again, it may do that with application servers as well. So if you're making a call and you're walking with it, this means service interruption. This means voice call interruption. That's really like very, very annoying, much more annoying than the post-dial delay. And as you move, even between operator regions here, between your home network and another roaming operator or an alliance with the home network, this will require having their PCRF talk to your home PCRF here to authorize you at your home network because it doesn't know you or have your profile. And their AAA talking to your home AAA, authorizing for at its level, at the AAA level. So that takes quite a long time. So the solution to that was through simply what we proposed is really pre-authenticating. Before you really move here, we predict that you're going to be moving, if you become on the bordering cell, if you're on the border between two networks, then we trigger sending, pre-authenticating you with your home operator, so you won't have to do this signaling when you really want to hand off. So that's the whole idea. This is kind of different from current attempts. We were the first actually to propose pre-authentication to IMS. This is different from the current attempts to optimize pre-authentication for mobile IP, which is taking place today in today's in the IETF a lot today. Because we have this variability, actually going back to the same question that we had, there might be so many providers giving you this service, and it might take quite a long time actually to acquire the service. So we do this pre-authentication to save ourselves from that. So the simple idea is basically once you authenticate and you establish your session, right before it, we send the time that is required for authentication down to the AAA server. And the AAA server, once your session starts, forwards that to your radio network controller because it really sees and knows which cells you are in. So it knows if you're handing off soon or not. So once you're really about to hand off here, The radio network controller will send the handoff imminent message up to the AAA, and from the AAA will send the expected target PDSN up to the PCRF, the PCRF telling it, hey, the user is about to hand off to this target PDSN, pre-authenticate him there. So this PCRF immediately forwards this information, like acquires if there is any authentication with the application servers, and pushes that information to the PDSN even before you're there. So that's simply a pre-authenticating you there. And then once you really hand off there, doing the same procedure as we showed with the call setup, you simply don't have to do this IMS authentication at all. So we did it right before this mobile IP signaling is taking place. We did it right before you come. The idea and the clean thing about this approach is that we only used policy servers, the policy framework to bypass these triggers. We didn't need to introduce any other components. So the policy framework is what really ended up forwarding these triggers from one component to another. And that's the novelty of our approach here. The final challenge I wanted to talk about is if we have multiple networks, multiple bearers in our network, UMTS, WiMAX, EVDO, we're imagining in the future some situations where I want to break up my session if I'm engaged in a voice video call over EVDO, which has quite a narrow bandwidth compared to WiMAX, right? So if I hit WiMAX, I can keep my VoIP stream connected to EVDO in order to avoid interrupting the current session, and split the service with the WiMAX. So this service splitting doesn't exist in today's semantics. So that's one thing that we're working on currently. The lesson learned finally from this whole research is that it's not really that simple, actually, to deploy services. Quality of services really needs to be integrated into the network and really needs to be part of our original design of the network. We need to consider things from an end-to-end approach. We don't need to just design things haphazardly. And optimizations are necessary at each tier in the network. They're not necessary. You cannot do optimizations just in the RAN and leave the other parts. You have to have a comprehensive picture. Especially as an application developer, you really have to expect these interruptions. You have to understand what's happening, what's the underlying things that are really happening inside the network. And more sophisticated things that will happen in the future, as I just mentioned, splitting services and these kinds of things, you really have to be aware of what's happening there, whether you're accessing WiMAX, EVDO, and what are the semantics of the underlying networks that are taking place. Thank you very much, and I appreciate very much your time, and I welcome any questions.
Could you use GPS to optimize some of the handoffs? Would it be possible to use GPS to optimize some of the handoffs between cells? If you could tell where somebody was and how fast they were traveling, what cell they're heading towards?
Definitely. I recently, actually, through the 802.21 standard, this media-independent handoffs, people were proposing actually using location-based predictivity through GPS. The issue actually is there are many issues actually with GPS today. I was just listening to a workshop in the last conference, this Consumer Electronics Conference, CCNC in Las Vegas. People were talking about the accuracy of your GPS fixes. They're called fixes, where you're acquiring or basically acquiring information from the network. And there are some locations that it becomes very hard to acquire the exact information about where you're exactly located. It's possible, but people are still working on it. The most dominant thing today is really your signal-to-noise ratio. But definitely there is a lot of room about it. I've seen something with people using TV signals to locate you, to do the triangularization. So that's a very cool application of it. And I think that in the future, GPS will be probably one of the ways to go about this predicting, about accurately predicting an imminent handover. That's definitely one of the things that are highly considered today.
Yeah, I guess QoS for telecom networks are important, but I guess IMS particularly, I guess, go one step further because it actually correlate this with application. So I guess there's been concern about what it is to do with net neutrality, for example. So do you have any comment on that?
Can you repeat the question?
Yeah, basically the net neutrality, because potentially the telecom, the ISP providers, the wireless providers, they can basically, control the traffic in a certain way to, benefit whatever their business, based on the content and the application, as opposed to just generally based on the condition of the network and the users.
So this is a very important issue, if I understood the question quite well. So it's more about differentiating the services rather than thinking of considering services as just flat IP based. Is that the part? Yeah. So definitely, the whole point about IMS is basically to do this service differentiation. So when we say quality of service now, okay, what we learned today, well, it's not simply diff serve, it's not simply int serve models that we all study about in the books and textbooks. It's much more than that. SIP is basically configuring things for us and really configuring the parameters for diff serve and int serve in reality inside the IP network, configuring the radio access network somehow to basically establish the quality of service requirements for your service end-to-end inside the network. So the game that telecom providers are playing, they're really avoiding the mistake or what happened with the regular internet service providers in deploying and really charging for the quality of service that they give to the customers through that signaling and giving them better experience. Does that answer your question? Thank you.
So I know you all are probably hungry, so feel free to go at this point. And if anyone else has any questions for Saeed, please stick around and feel free to ask those.
Thank you very much.